All right, so yesterday we were looking at these logistic functions in terms of solving the differential. Okay, it took us kind of a while to do that yesterday. I told you guys, bless you, that you don't have to remember that whole process, but I just wanted to show you if this is the differential for a logistic function, we also have this solution curve to the differential, aka separating the variables, solving for y. We spent a great portion of yesterday doing that. Do we remember doing that? Okay, I wanted to show you where this came from, not just giving it to you guys. So what we're going to do today is just take a look at a bunch of different free response type questions that involve these logistic growth equations. Before we tackle the first one though, we're going to pay close attention to an inflection value, okay, a point of inflection. If you take a look at the two equations in that box, okay, the differential equation and the solution, do you notice how the variable L kind of plays a key role because it shows up in both of them? Do we remember what that L represents? That's your carrying capacity or your limit, the highest amount. Okay, so in terms of a graph, if I tried to draw one fairly quickly here, there's going to be some limit, and as the logistic function grows, it's going to reach that carrying capacity and never go past it. Okay. So in terms of this carrying capacity, maybe we can figure out the inflection value, okay, where the slopes are increasing most rapidly. Okay, so that we're trying to figure out that point of inflection where we change concavity. Notice how the first part of our graph is concave up, and then it changes to concave down. So we have something going on right there as a point of inflection. Where does it look like that point of inflection is located on the graph? Maybe in relation to your carrying capacity. Somewhere right there. Where is the location of the point inflection related to the carrying capacity? Yeah? It's halfway, okay? So we can say the point of inflection is halfway to the carrying capacity. So if you know the highest amount of something, like your population or your value, you can figure out exactly where it's increasing the quickest. Okay, it's going to be halfway to that point. Okay, so we might have to use that idea as we go through some of these free response questions. Okay. So take a look at number 6 here. The population of Alaska from 1900 to 2000 can be modeled by the following logistic equation. I know it's kind of small on my board, but you have it in front of you, right? Can we read that little number? Honestly, no. Okay. Yeah, negative 0.0516 t. So what I want to do is first identify, is this the differential equation or is this the solution equation? And once we can identify which one it is, we're then going to label what these different numbers represent. Okay, so take a look at the box at the top. Are we dealing with a derivative equation or a solution equation? Yeah, a solution. Okay, so it's going to look like this one. Y equals something, okay, P of t equals something. All right, so if we take a look at the way this equation looks compared to the format of the solution we did yesterday, what is that 800,000 number representing? That's your carrying capacity, right. What about the 71.58 value? That's your C. And then that wee little itty bitty number, what does that represent? Yeah. Negative LK. Yeah, right. So I guess the number itself just represents LK. Good. Okay. So if we can identify those different values, we can maybe use them in these questions if needed. Okay. So let's go ahead and check this out. P is the population and T is the years corresponding with a beginning time of 0 for 1900. Okay. So that might be interesting to just note there. What is the predicted population of Alaska in 2020? This is a calculator active question. Notice how crazy those numbers are. Okay, we have a huge number and a decimal. How might we predict the population in 2020? What do you want to do, Caitlin? Say it again? Yeah, you, Caitlin, sorry. Mm-hmm. We are going to plug in a time.
You're starting from 1900, so you're going to have to figure out, so that'd be 120 and 13.
There we go. All right, so years since 1900, 2020 would be 120 years. So we're going to plug in 120 into that equation, that solution curve that's given to us. And we're going to figure out our population. Be careful how you use your calculator. Maybe you have to do things in steps. But you're plugging in 120 in for that little t spot in the power. Seven, 8, 1, 2, 1, 7, something, something, something. Let's go ahead and assume that we're going to take it to a whole number because you can't have 0.6016 of a person. So how many people? We're not quite 18, right? I mean, it would technically round to 18, but you're not there. So I think we're going to have to keep it at the 7.
What about like a double amputee, which are both the legs?
So you're telling me a double amputee is less of a person than a whole person? No. No. I understand where you're going though. In terms of a body.
Yeah, I think it relates to like pregnancy.
Oh yeah. So I'm double important. There we go. But I understand where you're going with that. All right. Let's check out B. How fast was the population of Alaska changing in 1920 and 1940 and 1999? What do we got to figure out for that type of worded question? What the derivative is. Okay, so we want to take the derivative of the P equation given to us and somehow plug in whatever time represents 1920, 1940, 1999. So let's go ahead and figure out those. 1920 is 20 years past 1900, and then we have 40 years past 1900, and then 99 years past 1900. So we got to find the derivative of the P equation and plug in 20, 40, 99. Do you guys want to do that by hand? You could. It's a quotient rule, right? Low d high minus high d low, square the bottom, and away you go. We do have a calculator. Do we remember how to find the derivative at a point on our calculator? Maybe. Let's try it. Okay. We hit the math button, and I believe it's option 8. It says deriv. So we want to find the derivative with respect to x. We're going to type in a little x in the first box. And then the function gets typed in inside those parentheses. So let's go ahead and type in the equation we have. Make sure you put the whole bottom in parentheses because we're dividing by all that stuff. Instead of t, we'll say we have an x. And the last little box we have to fill in is the x value that we want to plug in to evaluate. So for our first one, we'll just plug in 20. So we get 1678.078. Can we put the units on that value? Find how fast? Go ahead, Eric. People per year. If it's a rate, you need some type of per going on there. Miles per hour, feet per second, people per year, gallons per hour, something. All right, so we're just going to repeat the process for the other values. Maybe you want to use the entry capability on your calculator. If you hit second enter, it'll bring up the last thing you typed in. And that's convenient because instead of plugging in 20, we just want to plug in 40. We're going to change one number. And you can hit enter and it'll give you your new rate. Can you guys find the rate for 1999? There we go. Plus some decimals. There we go. Okay. We doing okay so far? Sure? All right. Whatever, right? All right, C. When was Alaska growing the fastest? Okay, when was its population growing the fastest? And what was the population at that point? How can we figure out where we're growing the fastest? Increasing most rapidly, yeah.
Okay, so if you're going from like 1900 to 2000, couldn't you just go halfway between that?
Okay, so it's not halfway through your interval.
Okay.
It's halfway of the carrying capacity, which is 8,95598 divided by 2. Half of that, 447,799. Okay, but this is representing people. Okay, that's your population. The question is asking, when was Alaska growing the fastest? AKA a time. We have to figure out a specific year. So if we know the population of when it's growing the fastest, how can we figure out the time at that point? What do you think, Caitlin? And for P of T. All right, so 447,799 equals P of T. Maybe we'll use our calculator to help us figure out that value. We can type in this in y1 and our function in y2 and find that intersection point where they're exactly the same. let's see, if we think about a window, we know the X-min is going to be 0. That's our starting year of 1990. And how many years since 1990 do you guys want to calculate up to? We can always go back and change it. You want to go up to 2000? We'll go 100 years. And maybe we'll count by tens. All right. The Y values, aka the populations, we're only concerned with seeing this 447,000 number. So as long as you choose a Y min and a Y max that has this value in between it, you should be good to go. So maybe we'll do 400,000 and then 500,000. You could do that. Or maybe you want to see the entire logistic graph. We could go from 0, and don't we know what the carrying capacity is, the most we'll ever have? The 895598 value. Okay, you can choose whatever you want there. And I want to count by 100,000s. Alright, so there's the start of the logistic graph. Notice how it's about to level off. And here's our point of inflection value, okay, halfway through. So we got to find that spot where they cross. Let's go ahead and evaluate the intersection. So it looks like our time value is 82.765. All right, so to answer the first question, when was Alaska growing the fastest? Alaska was growing the fastest at time 82.765. So about a quarter of the way through 1982. And what was the population then? What do you think, Caitlin?
It was the 447.
Mm-hmm. Good. Hanging in there? All right, last part, D. What information does the equation tell us about the population of Alaska in the long run? So as time goes on forever, what can we say about the population of Alaska? Yeah. It'll keep increasing. Okay, so in terms of our graph, let me go ahead and let's go a little bit further into the future here. Instead of going to 2000, maybe we'll go more. So we're going to increase, and then we're increasing at a decreasing rate. Okay, so we have that concave down. That's definitely one way to describe it. They're not really saying us, so you could say the population continues to increase at a decreasing rate. Do we know something specific about the population? Maybe we'll write down Caitlin's first. The population continues to increase at a decreasing rate. Is it going to continue to increase forever, though? What do you think, or Cameron?
It'll never get bigger than the 895,000.
There you go. But will never go above that carrying capacity. So that's like your max amount of people. We doing okay with our first free response? All right, let's go ahead and check out another one. Okay, so since we have this connection that we discussed between the differential logistic function and the solution curve, maybe we can convert between the two if we can recognize those different L values, C values, and K values to our advantage. We're going to take a look at number 7 here that might involve that. So let's take a look. The growth rate of a population of bears in this case is newly established, modeled by this differential equation, where T is measured in years. What is the carrying capacity of bears in this wildlife preserve? So somehow, based off of this differential equation, notice how it looks very similar to the differential setup for logistics. Can we identify the L value, the carrying capacity, from that function? Go, Caitlin. 100. So the 100 is representing L, and the 0.008 is representing that constant K value. That's going to change for like every problem. All right. What is the bear population when the population is growing the fastest? So if you said the carrying capacity was 50 bears in part A, what's the population when it's growing the fastest? That point of inflection. What do we think? 50 bears, right? The carrying capacity divided by 2. All right, let's check out C. What is the rate of change of population when it is growing the fastest? So what is the rate of change? We're trying to figure out a derivative, okay, a rate, specifically when it is growing the fastest. And we already said from part B that it's growing the fastest when we have a population of 50 bears. So how might we use that 50 to help us figure out the rate? Yeah. And for P, okay, that's your population at the specific time that you want it to be changing the fastest. So let's go ahead and figure out the rate, aka the derivative. Can we get 20? All right, what about units? The rate bears per year. All right, we doing okay? So it wasn't really necessary for this question, but I want to see, just to kind of practice this. Let's say if we had to do this, we could. They give us the differential equation for the logistic, and if we're able to label K and L, can we think about what the solution equation might look like? Let's see if we can do that. So the population equation, can we fill in specific values? Let's see, we said L, the carrying capacity, was 100, based off the way that differential equation looked. And then in the denominator, we don't know what C is, so maybe we'll just leave that the way it is. And in the power spot, we need negative L times K. So can we calculate negative 100 times 0.008? negative 0.8, yep, and then the t. Okay, so it didn't ask us to do that, but notice how we could fill in certain values based off of the differential. Okay, so that's good practice because we're eventually going to get to that point. Okay, let's go ahead and check out 8. Suppose that a population develops according to the logistic function where t is measured in weeks greater than or equal to 0. Okay, what's different about this differential function compared to the other one we just did? We don't have parentheses, right? Okay, we want the logistic differential to kind of have this setup where we have a k times a y value out front and then that carrying capacity minus the y value on the inside. So if you take a look at this one, we can think about factoring something out. Okay, we would take out or factor out that k and then y value. So what can we factor out of this differential? Can we think of a greatest common factor or a variable? Yeah. 0.002p, I like it. Okay, so let's think about that. If we were to divide out a 0.002p from both of those terms, what would we be left with? Let's see, 0.2 divided by 0.002. That would be 100. And then if we take out a 0.002p from a 0.002p squared, we're just left with p. You see how we did that? Didn't we change it now into the format? So we can identify the carrying capacity, and now we can identify that constant k value. If we had to, can we go ahead and write what the solution curve might look like? We have that L value divided by 1 plus the C value, we don't know that just yet, times e to the negative KL, so negative 0.2 T. Right? So we have a plethora of information here. Not sure what we're going to have to use or when we're going to use it, but let's go ahead and see. We'll tackle part A. If p of 0 equals 5, what is the limit as time goes on forever of the population of these, whatever population? They don't even tell us. Okay. What do you think? Yeah? It'd be 100. That's your carrying capacity. As time goes on forever, you're never ever going to go above that 100 population. What about part B? If p of 0 equals 60, if time goes on forever, yeah, it's still 100. Yep. What about C? As time goes on forever, what's your population going to do? So I know, it's still 100. It's still 100, okay? So what this is saying is it doesn't matter where your beginning value or where your beginning population starts, whether you have 5 people, 60 people, 120 people, or bears or whatever. The limit as you go towards infinity, as time goes on forever, it's always going to be that carrying capacity, okay, the most amount that you can have. What does change, though, is the graph of the solution curves. So that's what we're going to check out in part D here. So let's go ahead and draw a little grid. Okay, first quadrant. We know that the carrying capacity is 100, so maybe we'll draw in that most amount. Do we know where the point of inflection is? Where this population is growing the fastest? Isn't that 50? Okay, so that's where your point of inflection occurs. So let's think about if our beginning population was 5, wouldn't we be starting somewhere all the way down here? And as our logistic curve develops, we initially have a concave up graph because our population is increasing quickly. But then we're eventually going to reach that point of inflection where we change concavity and eventually are concave down, approaching that carrying capacity. Okay, so if you have an initial value that's less than the point of inflection, you're going to have that curvature going on. The next one, though, we have an initial population of 60, which is above that point of inflection. So what might the graph look like there? Yeah. It's just concave down. You're already past that point of inflection, so you're not going to have a change in concavity. You are going to increase, but it's always going to be at a decreasing rate because you can't go past that carrying capacity. Let's say we had an initial population higher than the carrying capacity. That means we're losing population, right? We're essentially not going to go less than 100. So what might the graph look like if we start there? Yeah.
Concave up, graph approaches 100.
There we go, concave up, but we are decreasing, approaching 100. Good. All right, so which one of these graphs has an inflection point? Which one are you able to say is growing, at what point the graph is growing the fastest? A, yep. Okay, graph A has the point of inflection. We hanging in there? All right. Let's see, I think the bell's going to ring in a little bit, so we'll save 9 and 10 for tomorrow.